Hi, welcome back to educator.com. Today we're going to talk about variation, both direct variation and inverse variation. Variation is a way of talking about how different things relate to each other. Depending on the type of the variation, we'll know what form the relationship takes. However, we should point out that variation isn't connected very closely to functions. While this sits in the section on functions, it's only sort of connected to functions. We can describe it in the language of functions, but honestly it's much easier to talk about it with equations, or it's much easier to talk about variation using equations, so that's what we're going to wind up using, that y equals stuff involving x, what we're used to from doing lots of algebra for. So that's what we're going to see for our variation stuff. In any case, variation comes up a lot in a wide variety of real-world situations, so it's important to understand. If you're interested in physics, chemistry, economics, astronomy, scientific fields in general, you're going to probably need to be familiar with variation. It gets tossed around in those fields. Also, it tends to show up on standardized tests a lot. Things like the SAT, the ACT, the GRE, all of these have a tendency to have one or two questions about variation, either direct or inverse variation. So it's important to know this thing in your back pocket if you're going to be taking one of these standardized tests at some point. All right, let's take a look at it. Direct variation. This is the simplest form of variation, but it's also the most common. Direct variation says that two things are directly related to each other. If one goes up, the other goes up. So if the red one goes up, we know that the blue one will also go up. Similarly, if the other goes down, if the red one goes down, then we know that the blue one also has to go down. They will go at different rates. For example, in this picture we've got here, the blue one always goes at a smaller rate and the red one goes at a bigger rate. It goes faster than the blue one, but they always go in the same direction. So direct variation is same direction. One goes up, the other goes up. One goes down, the other goes down. They're linked. They move in lockstep. We see this kind of relationship in a lot of situations. Here's a common everyday example. Say it costs you $2 to buy a loaf of bread. If you buy 10 would cost $20, but if you bought only 2 loaves, it costs $4. The more bread you buy, the more cost. The less bread, less cost. The total cost of the bread and the number of loaves you buy are in direct variation. It seems kind of obvious, but direct variation is actually a pretty simple concept to get around. It's just two things are linked. If one goes up, the other one goes up. One goes down, the other goes down. Direct variation. There's lots of different ways to say that two things, let's call them x and y, are in direct variation. We could say x and y are in direct variation. We could say x and y vary directly. Y varies directly as x, which is to say as x would do something, but we don't know what x is doing yet until later on, so it's y varies directly as x. X and y are directly proportional. Y is directly proportional to x. Lots of different ways to say it. But they all mean the exact same thing mathematically. In mathematics, it means y equals k times x, where k is a constant. So k is just a constant. It's called the proportionality constant or the constant of variation. It's the rate at which the two things are connected. Remember with the arrows, the red arrow is bigger than the blue arrow. There's some rate that says red arrow grows faster than blue arrow, whether it's going up or going down. In the previous example about loaves of bread, k would be representing the price of one loaf. That's the rate of connection between loaves of bread and the cost of the bread is the price. The price is what's connecting them. That would be our rate k for that loaves of bread example. It would be based on the price. All right. Inverse variation. The idea of inverse variation is the opposite of direct variation. Not a big surprise there. It says that two things are inversely related to each other. So this means if one goes up, the other one goes down. But if one goes down, the other one has to go up. So they're usually going to go at different rates. Once again, they have different growths in the red and blue arrow, but they're going in opposite directions. That's the really key idea to get across from inverse variation, is that in inverse variation, they go in opposite directions. If one grows, the other one shrinks. If one shrinks, the other one grows. And also, I want to warn you here. Inverse variation is not related to inverse functions. It's not connected to inverse functions. It's based on the idea of multiplicative inverses, those reciprocals like 3 and 1/3. 3 and 1/3 are multiplicative inverses because they cancel each other out. So that's what we're talking about. We're not talking about functions canceling each other out, that kind of inverse function. We're talking about the multiplicative inverse. That's where inverse variation is getting its term from. Right, this idea comes up a lot less in in everyday situations. We aren't going to see it with bread, but it's pretty common in the sciences. For example, consider gravity, right? Gravity is an inverse variation effect with distance. The force of gravity that Earth exerts is inversely related to the distance from Earth, right? The more distance you have from the Earth, the less gravity you experience. The closer you are to Earth, the less distance you have, the more gravity you experience. Gravity and distance are in inverse variation, right? One of them goes up, the other one goes down. If the first one goes down, the other one must go up. And technically, just so we have this, on the books officially, it's not actually distance that is the inverse, it's the distance squared, but it's the same idea. One is going up, the other one's going down, the other one goes down, the first one goes down, the other one goes up. Technically it's d squared, but you can learn about that in a physics class. Don't worry about that right now. Inverse variation, lots of different ways to call it out, just like direct variation has many names. We can say x and y vary inversely, y varies inversely as x and y are inversely proportional, y is inversely proportional to x, or x and y are in inverse variation. And we also will sometimes call the relationship reciprocal proportion, remember, because we're talking about flips, the 3 to 1/3 kind of reciprocal, or confusingly, sometimes, once in a while, you might hear somebody call it indirect variation. This is kind of weird because direct, indirect, but I think it's kind of weird. I think inverse and reciprocal, those really get the idea across much better than indirect, but once in a while, you'll hear people use that, so it's important that we're aware of it. In any case, even if it has all these different names, they all mean the exact same thing mathematically. Y equals k over x. And once again, k is a constant. It serves the exact same purpose as it did for direct variation. It gives the rate at which the two things are connected. How much is that blue arrow going to grow or go down, depending on how much the red arrow is changing, right? The red arrow and blue arrow on the last one where we talked about inverse variation, it didn't go at the same speed. They went at different speeds, right? The red one grew a lot and the blue one went down a little bit. The red one went down a lot and the blue one went up a little bit, so that we've got that same rate thing going on, this k. And if we wanted to, we could also see this as y equals k times 1 over x. That would be perfectly reasonable as well, but I prefer k over x just because it seems a little more compact. But they're really just equivalent statements. Okay. Joint variation. If we want, we could have multiple direct variations going on at the same time. If we want to do this, we use the term joint variation. So we could say z varies jointly as x and y, which says z has a direct variation with x and a direct variation with y. Or we could also say z is jointly proportional to x and y. So these are our two ways of saying it, but they're both going to mean the same thing. Z equals k times x times y. And once again, k is a proportionality constant. It is the thing that is linking the rates of change between various stuff. Now, real quick, you might wonder, well, wait a second. If z is connected to x by direct variation, then that would be z equals k times x. But then we've also got direct variation with y, so that's z equals k times y. So let's use a different letter. Let's call them k1 and k2, right? So k1 and k2 are both constants. We're going to need different constants because x and y are different things. So if we put these together, we'd really get z equals k1 times k2 times xy, right? We can put those constants together, k1 and k2. So why is it that it just shows up as just k as opposed to two constants? Well, remember, if k1 and k2 are both constants, then that means that when we multiply them together, k1 times k2 is constant as well. So if k1 times k2 is just a constant, then that means to heck with it. Let's just give it a new name and say k1 times k2 equals just k, and that's why we only have to see k there. It's because it's two constants combined into one constant, so we aren't going to have to worry about keeping track of two separate constants. We can just merge it into a single proportionality constant, and that's why we've only got the one of them. So if we've got direct variation, we've got joint variation, multiple direct variations going on at once. It's all of the things we're varying with one proportionality constant, k. Great. We can also combine multiple types of variation. We can stack direct and inverse variation if we have these sorts of relationships going on simultaneously. For example, here's a gas law from chemistry and from physics. You can probably learn it in both courses depending on how the course is taught. Given a fixed amount of gas, which is to say just air, like the kind of air in a room, not gas like gasoline, petroleum. Given a fixed amount of air or gas in a container, the pressure, P, of the gas varies directly as the temperature, T, and inversely as the volume, V. So the inverse thing would show up down here by the divide by V, and our direct would be just T. So it's K times T for the direct, and then K over V for the indirect. And once again, we put them together, and they just combine, and they become a single constant of variation. So we just get a single constant K. So we just put the various kinds of variation that we have, we just stack them all together, we do them all at once, and we put only one single constant K, and that'll be enough for the exact same reasons we talked about on the previous slide. All right, that's everything. We've got everything we need under our belt to get to the examples. A and B are in direct variation. So if A and B are in direct variation, we know A equals K times B. Or we could also write it as B equals K times A, but notice that they'll wind up having the same effect. When A equals 13, B equals 5. So let's plug this in. Let's find out what K is. As if we want to know what is B when A equals 52, we're going to need to know what K is to be able to figure that out. So we start off by figuring out what K is. 13 equals K times 5. So that means that 13/5 equals K. Great. If that's the case, we can go back and we have that A equals 13/5 times K. Now we plug in A equals 52 and we figure out for a different B. If A is 52, then we've got 13/5 times K. We multiply by 5 divided by 13 to cancel out that fraction on the right side. We get 5 over 13 times 52 equals, oh, whoops, sorry, not K. Screwed that up. A equals 13 over 5 times B. My apologies. So we plug in, now we're trying to figure out what B is. 5 over 13 times 52. 13 actually goes directly into 52. 52 can be broken up into 13 times 4. So we can come along and cancel this 13, and we get just 5 times 4, which is 20. So 20 is what B is when A is 52. Great. Next one, X and Y are in inverse variation. If they're in inverse variation, we've got Y equals K over X. We could also do it as X equals K over Y. They'll have the same effect. We'll wind up having different Ks, but the important part is we've got this setup of the inverse like this. When X equals 72, Y equals 3. So when X is 72, Y equals 3. Once again, we want to figure out what the K is because the next step is to figure out what is X when Y is 24. So we'll need that information about what K is. So X we put in as 72, Y we put in as 3. So 3 equals K over 72. Multiply both sides by 72. That cancels out the denominator on the right side. 72 times 3 equals K, which we use a calculator, and we get 216 equals K. Heck, you probably don't even need a calculator for that one. You might be able to do that one in your head. Y equals, replace the K now, Y equals 216 over X. So now we put in Y equals 24. So 24 equals 216 over X. So we want to figure out what is X. We multiply the X over on the left side, and we divide by the 24. We get 216 over 24. Probably want to plug that one into a calculator. And we will get X equals 9. And there we are, our answers. Great. Next example. P varies jointly as M and N. So what does that mean? Jointly as M and N means these two guys are going to be on the right. So P equals K, got to have that proportionality constant, times M times N. When M equals 4 and N equals 8, P equals 2. Then we want to find out what is N when P equals 60 and M equals 24. So once again, we need to figure out what is that K, what is that proportionality constant, if we're going to be able to figure out what N is in the second half of the question. So we plug in all the values that we know from the beginning. We've got P equals 2, 2 equals K times M at 4 and N at 8. 2 equals K times 32, divide by 32, 2 over 32 equals K. 1 over 16 equals K. Great. So with that information, we can now take this. We'll create a new thing that tells us the relationship in general. P equals 1 over 16 times M times n. Great. We know that p is 60. We know that m is 24 for the one where we want to figure out what the n is. So we plug in p 60 equals 1 over 16 times, we don't know what n is, but we do know what m is. M is 24 times n. Now notice, 24, there are some common factors between 16 and 24. 24 can be broken down into 8 times 3. 16 can be broken into 8 times 2. So the 8's cancel out, and we're left with 60 equals 3 halves times n. We can now multiply both sides by 2/3. 2/3 times 60 equals n. So now that cancels out the fraction on the right side. We can break down 60 into 3 times 20. 3's cancel out, and we've got 2 times 20, which is 40, equals n. So there's our answer. When p is 60 and m is 24, n has to be 40. Next example. All right, this one's a little more complex because it's a word problem, but we'll be able to work through it actually. Hooke's law connects the force of a spring to its compression. It says that the distance x is a spring. The distance x a spring is compressed or stretched from its equilibrium natural length is directly proportional to the force F of the spring. So first, let's wrap our heads around what that means. So very first thing you should do, if you read a word problem and you're not sure what a word means, go look it up. Either if it's one of the words that you learned because it was in that lesson, go check what that definition meant in the math, in your math book or from this lesson. Or if it's just a word that you don't know that didn't show up in the math before, just look it up in a dictionary. Like equilibrium, say this is a spring. Equilibrium is just what it is when it's at rest, when it's not being compressed or stretched. So it says that the distance x a spring is compressed. So if we push it in by some amount x, it compresses it. And then that causes the spring to push back with some force F. And this law, Hooke's law, says that the force F is equal to k times that distance. It is directly proportional, so it has that proportionality constant times the thing that it's directly proportional to, direct variation. So F equals k times x. Now once again, once we have that part figured out, it's just a normal problem from there on out. Say a spring is stretched by 0.1 meters and has a force of 95 newtons when stretched that far. And newtons is just the unit of force in the metric system, so just force. And then what force would it have if stretched by 0.25 meters? Well, 0.1 meters is just x equals 0.1, and force equals 95 for the first part of the problem. For the second part of the problem, we have x equals 0.25, and we want to find out what is the force. F equals question mark. So we see this diagram, we push the spring in by some amount, and that'll cause a force to appear in reaction to that where the spring is pushing back, and it will depend on the amount we've compressed it, right? If you take a spring in your hands and you push a little bit on the spring, it pushes a little bit back. If you push the spring really, really heavily, it pushes really, really hard back, and that's why we've got F equals k times x. How hard it pushes back is directly connected to how much it's been compressed or stretched. So what force would it have if it was stretched by 0.25 meters? To figure out that, we're going to first have to figure out what is k. So we do that by plugging in our numbers. So our force is 95 when it has been stretched by 0.1. So we divide both sides by 0.1. 90 over 0.1 equals k. So that just moves the decimal place over 1, and we get 950 equals k. So that tells us for this specific spring, the spring that this problem happens to be about, it has a constant of 950. It has a coefficient, a proportionality coefficient constant of 950. Technically 950 Newton meters, it's just it has units, but we don't have to worry about that. 950 equals k is perfectly enough. So 950 equals k is what it is for this spring. However, this is true in general for any spring. F equals kx is a very good rule for describing any spring that can be compressed or stretched. But this specific spring that we're working with has 950. A smaller, easier to push around spring would have a smaller k, and a harder, thicker, heavier, harder to push around spring would have a larger k. So 950 equals k for this one. So now we've got F for this specific spring, F equals 950 times x. So what is the x that we have for the second half of the question? X equals 0.25. So F equals 950 times 0.25. We plug that into a calculator, and 1/4 of 950 is 237.5. What's the units that we're using? We were told that the unit of force in the metric system is the Newton. So it's 237.5 newtons. And there's our answer. Great. All right. Last example. The maximum load a horizontal beam can support if held up at both ends is jointly proportional to the width of the beam and the square of its depth, while inversely proportional to its length. Oi, let's see if we can figure out what that means before we try to do this. So first of all, we've got some horizontal beam, right? So that we've got some beam, and it's being supported at both ends, right? It says maximum load a horizontal beam can support, so there's some weight in the middle of it, right? Some big heavy weight in the middle of it, and it's being supported on both ends, right? So it's being held up just at the ends, and it's able to support an amount. The maximum load is equal to, it's jointly proportional, no, sorry, not equal. The maximum load is jointly proportional to the width of the beam and the square of its depth, while inversely proportional to its length. So what is length, width, and depth? Well, let's take another look at the beam. We could have a beam like this, right? So its depth is how far down it goes. Here is D, the depth. We could also talk about what its width is. Its width is going to be, sorry, that was just me trying to make an arrow pointing at the W, but it wound up looking like a W as well. So width, jointly proportional to the width, and then finally the length of it there. Now, this makes sense. It would make sense that it's going to be inversely proportional, right? The farther out the beam gets, if we've got a beam like this, that's the exact same thickness and depth and everything, and we support it at the two ends, it makes more sense that it's going to be easier to snap it in the middle. The farther and farther we stretch it out on the sides, the easier it is going to be to snap it in the middle. On the other hand, if it's all the same thing, and it's a very short thing, and it's very stout, it's going to be able to support a lot more load if it's supported very, very closely like this. So that makes sense. It also makes sense that if it's wider, there's more stuff there. That if there's wider, it's going to be able to support more, and its depth, it's going to be able to support more. Now, it turns out that it's not just the depth, but the square of the depth. So we have to integrate that into our formula. So let's figure out how can we turn this into just a formula in math. The maximum load is equal to, first thing we have to do, we have to put in that proportionality constant, K. K times, so what is it? Jointly proportional to the width of the beam and the square of its depth, so times the depth squared, because it's the square of the depth, divided by, because it's inversely proportional to the length. So this gives us a formula for figuring out maximum load. We'd have to know what K is to be able to use this formula, but we've got a formula for doing that. All right, now let's continue with the problem and see if we can use that to figure out the rest of these questions. Okay, so now that we've got our max load formula here, if a given beam can support a maximum load of 750 kilograms, how much could it support if its length is tripled, or its width is doubled, or its length is doubled, its width is halved, and its depth is tripled? Uh-oh, wait a second. We don't have any information. Like the way we did all of these previous problems was they gave us enough to figure out K, and then we used K to figure out the rest of these problems. We don't have any specific numbers to work with, so what are we going to do? Well, the first thing we need to do is not freak out, right? We've got this problem, so there's a good chance that we can solve it. So let's just try the things that we normally try with word problems. Let's try to just name things that we aren't sure of at least. We don't have a specific number for the length that it is. A given beam must have a length, it must have a width, and it must have a depth at first, right? We don't know what they are, but we can still give them names. This is a great thing to do, is to just give names to the things that you don't know. So let's say right from the beginning, we'll name that its width, its initial width, Wi, its initial depth, Di, and its initial length, Li. So these all wind up being the initial width, depth, and length, respectively. Now, what do we know when we use the initial width, depth, and length, respectively? We know that 750 the maximum load is equal to K, we don't know what K is, times Wi times di squared over Li. Well, wait, we still can't figure out what K is. So what are we going to do? Once again, don't sweat it yet. Let's actually try some of these out. So first one, if its length is tripled. So if its length is tripled, we are going to have a different thing than Li, but it's going to be connected to Li, right? If we triple the length of Li, it's going to be 3 Li, so it's going to be 3 times Li. So what is it going to be if we've got K times W times di, whoops, not W, but di Wi over Li 3Li. Well, we don't know what that is, but oh, hey, that looks a lot like this. Oh, that's just a third. We can pull that third out, and we've got 1/3 times quantity K times Wi times di squared over Li. We already know what this is. That's just 750, so it's 1/3 times 750. 1/3 times 750 is 250. What's the unit we're working with? We're working with kilograms as our unit. So the maximum load, if we were to triple the length of this beam, would be 250 kilograms. Great, so now we've got an understanding of how this is working out. We just plug it in and we can use what we've got here. We can use the information that we've got. We don't have to know all the numbers. Knowing just one of them is enough because we've got a general form that it's working in. Width is doubled would be 2 times the initial width, Wi. So that would be K times 2 Wi times di squared over Li. So we pull that 2 out, we've got 2 times quantity K times Wi times di squared over Li. We plug in what we know that all is, that's 750. So it's 2 times 750, or 1,500 kilograms would be the maximum. Great. On to the last one. Ooh, this is a lot of things, right? Length is doubled. Length is doubled would mean 2Li. Width is halved would mean half Wi. And depth tripled would mean 3 di. Okay, so how does this come out? We've got K times Wi. Our new Wi is 1/2. Sorry, K times W. What are we using? We're using 1/2 Wi times d. What's our new d? It's 3 di, and this is important. So remember, we're not plugging in for just 3 di squared. We're plugging in all of this. It's what all the new depth is. And the new depth is 3 di, so it goes in parentheses, 3 di squared, so that 3 is going to get squared as well, divided by 2Li. So K times 1/2, let's pull the 1/2 down, and so we'll get Wi up here, but it'll be divided by 4Li. Times 9 di squared. So we can pull out the coefficients and we'll get 9/4 K times Wi times di squared over Li. We know what that guy is. That guy's 750, so 9/4 times 750. Plug that into a calculator and we get 1,687.5 kilograms. And there we are. One thing I'd like to point out is notice that depth by far matters the most because it's depth squared. So you can get a lot more load by just having a larger depth, right? You have to increase width a lot more than increasing depth because depth gets squared. This is why if you've ever worked in roofing or anything where you see a beam supporting a long horizontal length, if you get the chance to look up inside of an attic or inside of a roof, what's actually holding up the structures, you'll notice that the beams aren't flat like this. They're supported like this so that they can have the most depth because it's the depth squared that makes the strength. So they're always supported on a long, deep kind of axis because that gives them the most strength. So if you've done construction, you've actually seen this before. You've seen something where you're like, oh, what you're seeing there is mathematics in effect in the real world. Pretty cool. All right, hope variation makes sense, and we'll get started on the next section in the next lesson. All right, see you at educator.com later. Bye.